Most enterprise RAG systems rely on a specific pipeline. Take a PDF, pass it through a chunking algorithm, compress those pieces with an embedding model, and store them in a vector database. At scale, these embedding and top K nodes act as architectural bottlenecks. Professional documents rely on internal logic, like tables and footnotes, that flow across page boundaries. When we slice them into fixed-size pieces, we sever the dependencies that make the data coherent. We then try to compress that fragmented context into a single fixed-length vector. This forced distillation erases the nuance required to understand a multi-page technical argument. This creates a gap in retrieval logic. We rely on cosine similarity to find answers, which assumes that proximity in vector space corresponds to logical utility. In a financial contract, two paragraphs might use nearly identical vocabulary but carry opposite material meanings, one defining a liability and another defining an exemption. Vector search often retrieves the wrong one because they look similar on the surface. As long as systems rely on embedding bottlenecks, they hit a hard ceiling on accuracy. Faster databases can't compensate for retrieval that ignores document structure. To bypass that ceiling, we can model documents as hierarchical trees, nesting sections, subsections, and paragraphs exactly as they appear in the original source. Retrieval functions as a multi-step classification task, where an LLM agent navigates the document structure to locate specific evidence. This bipartite execution graph maps the logic from initial document ingestion to the final generated response. Phase 1 pre-computes the structure of unstructured files, while Phase 2 handles dynamic inference at runtime. Mastering this dual-phase system is the requirement for engineering agentic search systems at scale. Real enterprise file systems are chaotic. Millions of raw files sit in flat storage without any inherent semantic hierarchy. During ingestion, vision models and OCR parse natural document boundaries, avoiding artificial chunking. Topic models and LLM clustering then scan the ingested corpus to evaluate the actual content of every file. This process assigns multidimensional metadata tags. A single contract is linked simultaneously to its specific vendor, its geographic region, and its fiscal year. These multidimensional tags function as virtual nodes. They allow one piece of data to exist under multiple semantic ancestors, freeing it from the constraints of a rigid folder path. This ingestion step transforms flat storage into a multi-axis graph, ready for dynamic query processing. The runtime engine activates the moment a complex, multivariable user query enters the system. Unlike a standard file system, this engine does not query a static, pre-existing folder hierarchy. Instead, it parses the prompt to identify exactly which metadata axes are required to answer the question. The tree construction module pulls the raw virtual nodes from Phase 1 and visually stacks them into a bespoke hierarchy. This hierarchy is built specifically for the current prompt. Irrelevant nodes, like region or author, are excluded from the structure to focus the search space. Because the metadata tags were pre-computed during ingestion, generating this tree takes milliseconds. The retrieval space is now strictly conditioned on the query's exact intent, pruning irrelevant data branches before inference begins. With the tree belt, a traversal policy, an LLM agent, is positioned at the root node of the custom structure. At every node, the agent receives a specific input payload, the user query, the conversation history, and its current path in the hierarchy. The agent evaluates these inputs against the semantic label of the node it is currently inspecting. The LLM decides yes or no, should it open this subtree to find the answer. This logic gate approach replaces the mathematical proximity of vector retrieval with explicit reasoning. Retrieval is now a contextual process, identical to how a human expert scans a table of contents. Executing an LLM call at every node of a million-document tree would be computationally unviable. To solve this, a dynamic flattening routing fork splits the execution path based on the quality of the nodes. Path A activates when the child nodes carry rich, query-relevant semantic data. In this case, the system performs layer-wise traversal. The agent carefully descends the tree, using those labels to prune irrelevant branches. Path B activates when child labels are uninformative, such as arbitrary miscellaneous folders. Here, the system triggers recursive flattening. The entire uninformative subtree collapses, exposing the bottom leaf documents directly to the agent and bypassing the empty intermediate levels. This dynamic toggling keeps inference costs low by bypassing useless nodes, while preserving deep search where the context is densest. The traversal policy concludes when the agent reaches the relevant leaf nodes containing the target data. Because no chunking occurred during ingestion, the system extracts fully intact document sections. These sections and the user query flow into the synthesis engine. The LLM processes those intact passages alongside their hierarchical path data to generate the final response. Preserving the path data allows the system to output a traceable, step-by-step citation chain alongside the answer. This audit trail makes the model's reasoning transparent, providing a level of grounding that standard vector retrieval cannot match. The complete execution graph follows the data from ingestion to dynamic tree construction, through traversal and flattening, down to final synthesis. If you are building this system, the primary architectural mandate is to decouple document parsing from the search traversal mechanism. You will need an agents framework to handle the multi-step navigation logic, a distinct metadata layer, and an LLM API to evaluate relevance at each node. Adopting this graph completely addresses the accuracy problem of isolated vectors while scaling to massive enterprise file systems. True document understanding at scale requires moving the cognitive load away from static embedding models and into dynamic